Hello everyone, my name is Lulin Zhang. Today I'm going to present our work, SparseSat-NeRF or SPS Nerf, dense depth supervised narrow radiance fields for sparse satellite images. It aimed to generate synthetic images and DSM from a few satellite images. It is based on NeRF. It is a self-supervised deep learning method, and it doesn't need DSM as a ground truth. NeRF is presented in 2020, and it becomes more and more popular in photogrammetry and computer vision. It takes around 100 images for a small scene like this Lego. It considers the scene as a continuous volume with a different density in each point. It trains a network to predict the density and the RGB color of each point in the volume, and it accumulates all the points in the same array to get the pixel value, and use only the input image pixel values to supervise the training. As we can see, the resulted synthetic image is quite photorealistic. Even though NeRF is a pioneer work with a high-quality result, it is limited to several shortcomings. For example, NeRF considers outgoing light as emitted light, which means we can't change the illumination. It uses pinhole camera model, which is not the case for satellite images. It requires hundreds of input images, while satellite images often only have 2 or 3 images taken over the same area at the same time. After that, there are a lot of NeRF variants to overcome different shortcomings of the original NeRF, one problem at one time. For example, to make it work on sparse input images, work on satellite images, images in the wild, and so on. When we focus on NeRF variants that adjust NeRF to satellite images, there are only 3 publications, including S-NeRF, SAT-NeRF, and EO-NeRF. They all bypassed the problem of sparse input images by using multi-data images. S-NeRF improved NeRF by decomposing the outgoing light as albedo and incoming light. SAT-NeRF improves S-NeRF by integrating transient objects such as cars and using RPC models instead of pinhole model. EO-NeRF is published this year, and it used the geometrical shadow to replace the shadow predicted by network in SAT-NeRF. The key idea of our SPS Nerf is to combine SAT-NeRF with SGM and guided sampling to improve the result on sparse input images as few as 2 images. Firstly, I'll explain the part of SGM with our workflow step by step. Our method takes 2 images taken from different view angles as input. If we apply NeRF directly on them, the supervision would be insufficient for the training, which leads to unrealistic color in the synthetic image and the wrong DSM. If we follow the strategy of SAT-NeRF, which means to add sparse depth and uncertainty resulted from bundle adjustment for complementary supervision, we got blurry synthetic image and again wrong DSM. If we add the dense depth and the uncertainty resulted from SGM, we got a sharp image and a high-quality DSM. The dense depth is generated based on low-resolution image to improve the robustness. The uncertainty comes from the cross-correlation score. Now I'll explain the guided sampling. Before guided sampling, I'd like to firstly explain the basic sampling for better understanding. Here on the left, I displayed a training image. We selected a pink row to explain the details. On the right, I displayed the cross-section of the pink row. For each point on the row, for example, this yellow cross in the left image, we trace a ray from the camera into the scene, and we define several samples on the ray between the maximum and the minimum altitude of the scene. For each sample on the ray, we input its position and view direction to SPS Nerf to predict the RGB value and the volume density sigma. For each ray, we accumulate all the samples on the ray to get pixel value and depth. Multiple points can contribute to the color and the depth, with the nearer and the denser points contributing the most. Now let's go into the guided sampling. It is inspired by the similar idea from Roslow's paper to distribute the samples along the ray as a Gaussian distribution N. The mean value of the distribution is defined by depth, and the standard deviation is defined by uncertainty. Roslow's paper uses a network to predict the depth and the uncertainty for indoor scenes, while our depth and uncertainty is resulted from SGM. Finally, we combine both the basic sampling and the guided sampling points to accumulate for the color and the depth for each ray, and we use both color and depth loss to optimize our network. Now, let's move on to the experiments. We tested our method on two sets of datasets. The first one is DFC 2019 dataset. It includes multi-data worldview 3 images. We choose 2 or 3 images taken at the same time for 2 areas of interest. The second dataset is the Djibouti dataset. It represents a series of 21 multi-angular Pleiad images collected in a single flyby. We choose the 9th and the 11th image for training and the 10th for testing, and we use the cropped patch located in the center. Here are the results on the DFC 2019 dataset, AOI1, with 2 input images. The first row is the synthetic images, and the second row is the DSM. The last column is the ground truth. As we can see, compared to Nerf and the Sat-NeRF, SPS Nerf renders the sharper image and more informative DSM, thanks to our dense depth supervision. We also compare our DSM to the DSM resulted from SGM applied on full resolution input images. As we can see, the building edges and the roofs are more regular in SGM, as indicated in blue rectangles. However, SPS Nerf did a better job for buildings with a shiny roof, while our method produced the altitude similar to the ground truth, as indicated in green rectangles. Here are the results on DFC 2019 dataset AOI2 with the 3 input images. Same as before, our method rendered a more photorealistic image and recovered a cleaner DSM than Nerf and Sat-NeRF. Compared to SGM, our DSM is better at reconstructing vegetation and at handling building outlines near occlusions, while SGM is better at roofs and edges. Here are the results on the Djibouti dataset with 2 input images. This is less challenging than the previous dataset because it is a rural area without shadow and abrupt altitude discontinuity in the scene. For the synthetic images, we can see even the results of Nerf and Sat-NeRF are not bad, but if we zoom in, we can see the roads are blurry, while ours are sharp. For the DSM, Nerf and Sat-NeRF failed to recover correct DSM, while ours and SGM recovered DSM close to ground truth. Here we displayed a sub-zoom where SGM got a noisy result, while ours is more smooth without losing the details. Here is the quantitative result on MAE. Best and second best performing are indicated in blue and magenta. we displayed two sets of results, MAE in and MAE out. Here I displayed an example to show the difference. MAE in means valid pixels defined by SGM, and MAE out means the occluded and poorly textured areas. As we can see, SPS Nerf outperformed Nerf and SAT-NeRF in both categories. When compared to SGM, for MAE in, SGM achieved better value, which we can attribute to the irregularity of the planes in SPS Nerf. For MAE out, SPS Nerf has better results than SGM, which is consistent to the pictures we displayed before. That's all. Thank you.